Hello, everybody. My name is Ben, and I'm here to solve this problem for y'all. And I hope we learn something about ourselves and about mathematics. Uh, yeah. Anyway, this is exam 2, and we're looking at some Sherwood and Gillian relationships. For the following correlation, they put together this after years and lots of experiments, and it's valid over this range of Reynolds numbers. And I have a picture of it I can show in a second, but we are going to perform a dimensional analysis to establish these three dimensionless numbers, which I have Wikipedia pages up on. Those will come in handy later. And for the appropriate dimensionless groups, so we're going to perform a dimensional analysis to prove that. And then we are going to use a computer to generate some data points, and from that, give a correlation with some normal distribution, normalized error, rather. And and then we're going to build a model for it with two methods, and then we're going to plot that model. And it's going to be this nice, pretty 3D chart, and everyone's going to be happy, especially me, because I'm going to be finished with it. And so let's just go ahead and, oh, shoot, wrong screen. Here it is. So this is a picture of what's happening in this problem, right? We have a wet wall system. So basically, Sherwood and Gillian were trying to model the evaporative, sort of the evaporative mass transfer. So liquid is in a reservoir here, and it flows down the sides of the wall, and then as it flows down the sides of the wall, it's going to evaporate into some gas that's flowing up the pipe. So the gas is never going to become saturated because there's continuously more gas flowing up and up and up. So with that in mind, we don't just want to be able to solve this problem for just water and air, or just CO2 and water, or anything like that, because that wouldn't be very helpful. What they were trying to do, and what we're trying to do in this problem, is to develop a way to, across all kinds of densities and across all kinds of mass transfer coefficients between the two components, we're trying to find a relationship that works for everything. Hence why we're making these dimensionless groups, and etc. So dimensional analysis is a process by which we are going to come up with the relevant dimensions for some sort of problem. In this case, it's this wet walled tower. And we are going to use these dimensions to solve for some dimensionless groups. And then those dimensionless groups can be altered almost as like dependent variables of their own. And it'll let us learn a lot more about the system without having to do as many experiments. Now, obviously, we're not about to do any real experiments. We're going to use a computer and random number generation to do experiments. But still, I think we'll be able to learn some pretty cool stuff. So anyway, what are like some relevant dimensions for this problem? Well, probably the density of the water, right? Then I'd also say the viscosity is pretty important. Then also the mass transfer coefficient, right, this Kc. And then also on top of the Kc, we'd probably want this this driving force from the components, the driving force of A to B. And then, of course, the velocity of the water. And then finally, what are we going to want to have in here? We're going to need some sort of characteristic length. And this is something that you see in reflecting the Reynolds number. The characteristic length is kind of a reflection of, it's a little bit hard to explain, but basically it's almost the diameter of the system, at least in this case. So we're going to have a big D. Actually, I'm going to make it a little d because, we already have this big D for the driving force, so that would be confusing. So this is the diameter over here. So what are like the units for each of these? So we'll just put a U right here to mean we're looking at the units. Am I recording? I think I am. Yeah, I'm recording. So the units for density, that's just a mass over a length cubed, or a volume. The viscosity, well, that's mass over a length over a time, right? And then let's go ahead and do this driving. Sorry, that's my bad. Let's go ahead and take a look at this mass transfer coefficient. That's going to be a length over a time, right? It's it's kind of like how fast it's diffusing. It's kind of a reflection of that. Then we have this driving force. Driving force is going to be some sort of area, and of course area is length squared. and that's length squared over time. And then velocity, that's just a fluid velocity. Length, which I put as meters, we should do a length over a time. And this diameter is going to be a length. So now if we were to make a matrix out of these values, which we'll go ahead and do, we'll say length, time, and mass. Mass? Yeah, mass. So how many lengths are there? 3. I need to rearrange these. When I was practicing, I did it differently. I did it mass, length, time. Or no, I think I did it length, time, mass. I'm not certain. Anyway, it's going to really bug me if I don't do it that way. It's the way I was practiced it. So we got a 3. Oh, this is still not. I'll just do it. I won't like it, but I'll do it. So there's one mass here. There's one length and one time. That's easy enough. Then we got a length and a time, and no mass in the mass transfer coefficient. Now we have 2 lengths and 1 time, and I'll just go through and do the rest of these real quick, quietly, because I want to get these. I want to get through these. Nice. So now, basically what we want to try and do is we want to take the number of relevant sort of variables. So in that case, this is 6 minus the rank of this matrix, and rank is sort of a mathematical function that's pretty important to what we're trying to do here. And that's going to give us the number of dimensionless groups. So we'll call it the number of DMs. That's fun. Trying to talk in the DMs and like the group chat or whatever. I don't know how any of that stuff works. I'm not cool. So, yeah. So we need to get the rank. Well, we could solve that by hand, or we could just go to Collaboratory, and it has a function built in to do that. So this is the plot we're going to build at the end, kind of a sneak peek. I'll take a look at it in a second as well. But, yeah, so we're going to do linalg.matrix, and then we want rank. And this is just a rank solving function. So now we just need to put in our matrix, and I will go split my screen in half so it's easier for me to see it. Let's see, the first set on the matrix, the first kind of row is going to be, it's going to be a 3, comma, 1, comma, 1, comma, 2, comma, 3, 1, 1. Okay, here's a better way to view it. I was having a hard time viewing that. So we got 3, 1, 1, 2, 1. This is hard for me to type. Yeah. So next up, we have a 0, 1, another 1, then a 1, then a 1, then a 0, and then we go on down one last time, and we got a 1, and then a 1, and then a 0, and then I can't. Yeah, so this is our matrix. I think I typed this in wrong, but yeah, I didn't like it. It's probably because I didn't put parentheses where I was supposed to, so shame on me for not doing what I was supposed to be doing correctly. Yeah, so you got to put some parentheses to kind of define each of the columns or each of the rows in a matrix. So I think now that I've done it this way, yeah, we got the rank. The rank is going to equal 3. So the number of dimensionless groups we're looking for here is 3, because 6 minus 3 is 3. So we need to define 3 dimensionless groups, and we'll go ahead and we'll just go ahead and do that, right? So the first dimensionless group, let me pull paint all the way out. I think that would be helpful. Yeah, the first dimensionless group we'll call pi 1. And I'll define pi 1 real quick, and then I'll explain what any of pi 1 or anything like that means. So the way we define dimensionless groups, what even is a dimensionless group? A dimensionless group is a group of variables arranged in such a way to where it's dimensionless. So all the units cancel out, right? So we need to find a way to create 3 numbers that are all dimensionless where all the units cancel out. Well, let's see. The best way to do this is basically to create a core group. So to take any three of these variables, and really any of them works, as long as within that core group, every single unit type, length, time, and mass is represented. So, which ones to choose? Which ones to choose? Well, I'm just gonna go ahead and pick density. I like density. It's my boy. And then, in addition to density, let's go ahead and we'll pick up the yeah. Let's go ahead and get the what is this? I'm so sorry. The driving force from A to B. I couldn't say that all of a sudden. And on top of that, let's throw in the diameter. So between that, we have mass, length, and time all accounted for once. Now that we have this core group, we're going to put that core group in each and every single one of the dimensionless groups. So I'm just going to copy this and put another pi right there, and another pi right there, and then we can just go in and scroll over and go ahead and get out the handy dandy eraser, and we'll make that one pi 2. And my handwriting is kind of atrocious here. My handwriting is not very good in, it's not even very good in person or on paper. So you're having me write in paint, and I just chicken scratch. But I think I've gotten a lot better after practicing this a few times, so I'm feeling pretty good about it. And now to each of the dimensionless groups, we need to add in one of the variables that we haven't already used. So Kc, or the mass transfer coefficient, is one of the variables we haven't used so far. We haven't used viscosity, have we? No, we haven't used viscosity. We also haven't used velocity, I think, right? Yeah, velocity, I think. Yeah, velocity. It's, yeah, it gets old. So we'll put velocity and then finally viscosity. So, yeah. Now, we're going to take each of these to a power. In the core group, each one gets taken to a certain power. So, and then we're going to solve those exponents so that each group is dimensionless. Because right now, if each of those exponents were 1, these units wouldn't be dimensionless. They would have actual units, and then we wouldn't be able to use them very well. So with all that in mind, let's go ahead and try and solve it for 1. So let's see. Let's just write out all the units. Maybe that might be helpful. So the units are going to be density. Density is mass over length cubed. This DAB, or the driving force from A to B, driving force is just going to be length squared over time. And that's just going to be a length, right? And then Kc, or the mass transfer coefficient, that's going to be a length over time. So, how should we deal with this? Well, first off, we know we have to take B, it has to equal -1. We need to flip over the diffusion coefficient. And we need to do that because there's only one time in the whole formula. So in order to get rid of that time, we need to flip that over. Now, density we actually know is going to have to equal 0 because there's no other masses to cancel out the density here. So we know A is going to have to be 0. So that kind of leaves C pretty easy to go ahead and solve out. So if you look at it, we can just leave C as 1 because there will be 2 lengths on the bottom from this length squared being on the bottom to cancel out the time. And yeah, it'll all work itself out. So pi 1 is going to be let's see, we're going to have no density. We're going to have this mass transfer on the bottom. Not mass transfer, diffusion, driving force on the bottom. And Kc is, of course, on top. And then, of course, we're going to have the diameter, or the characteristic length. And, yeah, that's awesome. So I'm actually going to just go ahead and take a look at this real quick. If we take a look right here, we are going to see that, and I use different letters than they did here. But actually I didn't. You know what, I'll just save this bit for the end, because I'm a little bit confused about it, and yeah. So, now we have that. Let's go ahead and select this. Copy it over here again. And now we're multiplying it by velocity. Well, what is velocity? Velocity is just going to be a length over a time. Well, let's see. We need to have density be equal to 0 again, right? Because there's no mass. We need to flip over the diffusion coefficient again. And actually, if you look at it, these two things have the same units. So it's all going to be the same. So, but now it's velocity instead of that. So we go ahead and we can just say that pi 2. That was way too long of a line. That's more like it. Yeah. So our second dimensionless group is going to be the velocity times the characteristic length, the diameter, all over the driving force. And now pi 3 is a different unit because viscosity is a totally different unit than that. So we'll go ahead and actually, I think I still have this. Yeah, I still have it on my clipboard. So what's the units on viscosity? Viscosity is going to be, yeah, look at that, viscosity, a mass over length over time. So I'm writing with the select tool. That's fun. So now we know we're going to need everything. Well, we're going to have to flip over density, right, to cancel it out. So A is going to have to be -1. We're going to have to flip over diffusion coefficient too, right, to cancel out this time. Or why do I keep saying diffusion coefficient when I mean driving force? There's not even a diffusion coefficient involved here. This is the driving force. So driving force, driving force, driving force. That's maybe a way of convincing myself. Do I look good in the camera? I'm getting a little bit close if I get right there. So let's see. We have yeah, we gotta flip that over. So B is going to be -1. And then let's see, what would C be if we had all this all together? Well, we have one length left. So we would have to have, there'd be a length on top, there'd be three lengths on the top, 3 lengths on the bottom. Well, shoot, we can just set C equal to 0 here because we don't need it. You know, it's just getting in the way. So if we go ahead and solve that out, we will find that pi 3 is going to be the density. Actually, no, it's going to be the viscosity over the it's gonna be the viscosity. I'm sorry, I'm losing track of all my stuff. Over the density, all multiplied by the driving force. So, yeah, with all that in mind, we can actually find some dimensionless numbers in this. So, what is the Reynolds number? Actually, the Reynolds number isn't going to be very helpful here. We have the Schmidt number. Okay, do any of these look like the Schmidt number? Well, not this, not 1, not 2, but 3. Oh man, look at that. It's the same thing. So, pi 3 is the Schmidt number. That's one of our dimensionless groups. Well, pi 2, that doesn't look like any of the numbers. Actually, let's go ahead and look at the Sherwood number real quick. Pi 2 is going to be, did I do the math properly here? Well, oh, you know what? I did, because the way they wrote the Sherwood number here is kind of weird, because it's the diffusion rate divided by that L, which you're bringing over to the top. H is the same thing as Kc here. So we know that this, this one is the Sherwood number. Now this is actually something called the Purcell number. But, interesting fact, the Reynolds number is equal to the Schmidt number divided by the Purcell number. So if we were to do all the math, we would end up seeing that the Reynolds number is going to be equivalent to the there it is. Now we're going to have the density times the velocity times characteristic length. Now in this case, the characteristic length is going to be the diameter all over the viscosity. That would be pi 2 divided by pi 3. So I'll write that in. Pi 2 over pi 3. So yeah, now we have just proven that the Sherwood number, the Reynolds number, and the Schmidt number are the appropriate dimensionless groups for this problem. So with that in mind, let's take a look at the plot we're going to build. So each of these points is a randomly generated data point, and this is basically saying we ran an experiment, and in this experiment we kept track of those 6 variables, right? The 6 variables we defined over here. And we took these 6 variables, and we, how do I say this? We took the 6 variables, and we controlled them, and we kept track of them for a certain liquid and a gas, and we calculated, using those 6 variables, the Reynolds number, the Sherwood number, and the Schmidt number. Well, yeah. So that's actually not a great comparison. It's only semi accurate. When I really think about it, I had to think about the words I just said for a second, and that's actually only a semi-accurate comparison. How much time have I used? 20 minutes. That's a pretty good amount of time. So we're going to build this plot. We're going to build a grid to sort of be the trend line. And yeah, as you can see, there's some code here. You can take a quick look at it. But I'm going to go ahead and file new notebook. Get a new notebook going. Oh man, it feels bad. So we'll just call this one Exam 2. We'll star it just in case I need to take a look at this later. There's something wrong with the tab or something like that. And yeah, so Exam 2. We already performed this dimensional analysis. Well, the first step is we need to generate 100 pseudo-random data points. To do that, we're going to have to use something called numpy. So we're going to import. I can't spell anything today. Numpy as np, and that's just a standard way of abbreviating numpy. So yeah, we're going to generate 100 pseudo-experimental data points. So let's generate the Reynolds numbers first. So we'll say the Reynolds numbers equals numpy dot random dot shoot, see? Look, I can't write today. Uniform. And what this random uniform does is it's going to, based on some parameters we give it, generate a bunch of random values uniformly. So instead of having, say, a normal distribution, they're going to be uniformly distributed. Now this is important because we're going to add the normalized part of the function later. So we need a low value. Well, what's the range of Reynolds number from 2,000 to 35,000? Yeah. So that would be our range. And this last one, what is it called in there? It's called size. Size is just the number of data points we want to generate. So then we're going to take that. We're just going to copy it real quick, paste it down here, and say, actually, now we're doing the Schmidt number now. That one goes from 0.6 to 2.5, if I remember correctly. I got to check that. Yeah, 0.6 to 2.5, and we also want 100 data points. So now we need to calculate some theoretical Sherwood value, and we're actually going to calculate it just from the given function, because this is something that is basically just the way nature would behave. That's what this formula shows. It's not some... it was derived by people, but it was derived with lots and lots of experimentation. So we're just going to say that's like the objective way. But this is the theoretical Sherwood value. This isn't what we actually got in our experiment. What we actually got in our experiment is going to have some normal error. So we're going to have to use another random function. But this time it's going to be normally distributed error. Yeah, normally distributed error. So the location, that's like a mean value for it. the scale. The scale is a standard deviation. It's it's a measure of the standard deviation. The size is just given to us by what we already have. So the average is just going to be the theoretical Sherwood number, right? The scale, that's a little bit harder. It's going to be the theoretical Sherwood number times 0.1 because we need to add a 10% normally distributed experimental error. So this is how we're kind of spreading it out by 10%. So we go through, and I'll just take a look at what we get for the Sherwood number. So that's pretty good, right? It's kind of hard to see this without graphing it. But if you look at it, like there's some error, right? It's not just it's a bunch of random values multiplied together. But there is some error added in, and that's not really something you can really see unless you've looked at all of them, all the values we just gave, or if you looked at the Reynolds number and the Schmidt number and compared them. But let's run this again, and you're going to see, oh shoot, I should have left that up. We're going to see you get a totally different set of values, right, every time you run this. So we run it again. You get 118 as the first value. 42, that's pretty low, but this is all just randomly generated, just done by, I assume, atmospheric interference or something like that. Something just that's basically unpredictable as far as we're concerned. So, yeah, let's go ahead and plot these things. So, to do plotting, we are going to import this library. We're going to import this thing called Plotly, and the first thing we're going to do is import graph objects. And that is going to be imported as Go. That's just a little abbreviation for graph objects. You see GO. And oh man, no, not global. I said GO. I was fine with it. It didn't like that. So, and then we need to, from plotly.make, or plotly.subplots. This is going to allow us to, this is going to allow us make subplots. So we run that, and we go down here, and we're going to say figure. This is just the name of the figure, and that's just going to be make subplots. We're going to put some parentheses, but yeah, this is just defined some figure. And now we need to take the figure, and we need to give more, we need to kind of almost append it. So we're going to do fig.add trace. Oh, it's not following me. That's not good. Something hasn't been imported correctly. I don't know. We'll just have to see what happens. So we need to add something to the trace. Didn't like that. Why doesn't it like it? Well, we'll just go on and see what's going on. And maybe I'll have to look at some documentation to figure it out. So in order to add a trace, we need to, we need to have some sort of trace. You know what? I need to figure this out. Why is this not working? Okay. You know what? It is working. It just doesn't want to. Sometimes it comes up with documentation. Sometimes it doesn't. And if it doesn't, then I just assume the documentation isn't there. But the documentation is there. Or it was imported properly. So I don't know. That's just a little bit frustrating. I don't know why it does that. It takes a while to do that sometimes. But it needs a trace type. So we're going to, from the library graph objects, import this, or use this scatter3d function. Scatter3d has a lot of arguments. Basically, what it really wants, what it all boils down to, is it needs an x value, it needs a y value, and it needs a z value for each one, because it's a three-dimensional plot. So, because it needs our numbers, we'll go ahead and get rid of that, run it, just so we don't have that big thing in the way. Well, our x value, let's just go ahead and call that the Reynolds number. Our y value, let's just go ahead and call that the Schmidt number, and our z value, we'll call that the Sherwood number. Now let's just go ahead and run this and see what the plot looks like. We're going to get something, it's going to be kind of ugly, but it will get the point across. So these are all our points. You'll see they're in a three-dimensional plot. But there's a lot of issues with this, right? First off, all the points are plotted correctly. It did that good. But if you look at, there's all these lines connecting it. And that's because Plotly just assumed that the order of these points was important. But in reality, it's not. We just generated them randomly. The order, which experiment we did after which experiment, doesn't matter at all. So we need to get rid of these lines. Also, I like to make these markers a little bit smaller. And then also I want to label the axes. And I might change some colors and stuff around later. Who knows? That's for me to know and for you to find out. So we're going to say mode equals, and then markers. And then we're going to get this thing marker. Let's see if I can spell marker. I can. Marker color. Actually, I don't need really. Marker size would be a more important thing to modify. So we're going to get this marker size, and we'll set that to, I found that 5 is usually a pretty good size. And then we also want to relabel the axis. So we're going to change fig once again and something else, but this time we're going to do updates and then layout. So the way we're going to do this is we're going to use scene, and we're going to set this scene equal to a dictionary of data. So this dictionary of data is going to have 3 things in it. It's going to have, for each of the axes, so it's going to have x-axis title, and we're going to say the x-axis title should be equal to Reynolds number, because we imported the Reynolds number. Now I'm going to copy that, comma and paste, and then comma and paste, and then we'll just change it real quick for the y-axis, and now we need the Schmidt number. Should be SC, I think. I don't want it to be all caps. And then the z-axis, and that would be the Sherwood number. So let's go ahead and take another look. We'll run this again, see if this plot is a little bit more clean, a little bit easier to follow. And I would definitely say it is. I mean, we have our 100 data points, and I know it's hard. That doesn't necessarily look like 100 data points, but it is. To me, I always look at that and think, that's not 100 data points, but I'm pretty sure it is. I haven't counted it, but I mean, the code is correct. Like, it's not wrong. So, yeah, that just goes to show kind of why our intuition isn't always the best thing in the world. You know, that's an important lesson to understand, is that intuition, well, it's very helpful, and one of the greatest parts about being people, sometimes our intuition, especially about complex mathematical things, is wrong. And you have to keep that in mind whenever you're solving some sort of complex engineering problem. So with all that in mind, we have our data points. They're generated. It's clean. I like it. We want a trend line, right? If you remember what I saw, we had a grid going through here. But before we do that, we need to generate a trend line, because let's go back to the problem. And before we go back to the problem, I'll start a new code. And let's just go back to the problem. This correlation that we got from Sherwood and Gilliland, that's basically just a reflection of something happening in nature. We no longer know that anymore. That's not in our head anymore. I had it up above. We're going to pretend like we don't know that. Instead, all we know is that the correlation between these 3 variables is going to be something like some constant, A, times the Reynolds number to the power of some constant B, times the Schmidt number to some power C. And that's all we know now. So we have to figure out some way to build basically a correlation for this. So yeah, we need to build some sort of trend line. So first things first, we should linearize this formula, right? Because things are always easier to simplify if you linearize them. So let's just go ahead and linearize. But how can we linearize something when we have these exponentials and things are multiplied by each other? How can we go about turning that into a linear function? The way we can do that is by taking the natural log of things. Now, you'll note this NP log. Currently, it's commented in NumPy. There's this log function, and when the log function is log base e. So that's natural log. It would be like ln of whatever. But that's not what we're using here. We're using np.log of this Sherwood number is going to be equivalent to, well, we have to take the natural log of this whole side. So we're going to get the NumPy log of that. Then we're going to add it. This is a mistake that I made several times while I was practicing this. So we're going to take the log of A, and then we have B times the log of the Reynolds number, plus C times the log of the Schmidt number, right? So that's how we linearize it. Now this is a linear function. I mean, this could be modeled, this would be like y equals m plus uh, constant times, or y equals b plus m1 times x1 plus m2 times x2. That would be kind of how we would visualize this. But now what we need to do is, based on this linearized function, we need to do a linear regression with the Penrose pseudo-inverse. So what does the Penrose pseudo-inverse say? Well, that's a great thing to explain over here in Paint. So I'm going to save this. I'm going to do File, New, and I'm going to call this new file. I'm going to go ahead and call it, how much time have I gone through so far? 35 minutes. I'm doing really great on time. I'm really happy about that. I'm going to set up something everybody knows and explain it for this, and then we'll see if we can't solve it. So let's say we had something that fit the trend line y equals mx plus b. Well, we could represent this with matrices, and the way we would represent this with matrices is, let's say we had 5 points each. Or actually, you know what? Let's just say we have lots of points. We would say, basically, that, dadgummit, I think I need to select this, move it over here. That gives me more room. So I think, I'm still trying to write with select. Shame on me. So, yeah. And if we set up a matrix like this, where we had, say, all of our x values we found experimentally, and then a 1, and this is called a design matrix, and we multiplied it by a matrix of the constants, then that would equal a matrix of our solutions. So we have y1, y2, y3, dot, dot, dot. Dot, 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 dot. And this would all be 1s because b is a constant. B isn't changing over time. Now, we could use this to solve for the constants, right? If we didn't already know them. We'd have to multiply in some transposes, but we could definitely do this. We'd have to change the size, because currently this is, say, like a 5 by 2. This is a 1 by 5. So we'd have to multiply in the transpose, which a transpose is basically, let's say this matrix is 5.2, the 5 by 2, the transpose of it is going to be a 2 by 5. And that just lets us change the size of this matrix and focus in on the details we really want to focus in on by kind of averaging the points almost. It's a little bit hard to explain, but basically we could work all this out and we could put together a matrix of the constants, and it would equal these things. So, yeah, what would it equal? Well, let's go ahead and write it out. So, the matrix of the constants, and we'll just call this constants, is going to equal the numpy, where it's going to equal the matrix inverse. So, this lineage inverse is the matrix inverse, and it's going to be some design matrix, the transpose of the design matrix multiplied, and that at symbol means a matrix multiplication. Actually, that's an important thing to keep in mind. That is what that means here. And then we're going to, multiply it by the transpose again, and then multiply that by the, my voice is kind of getting a little bit sore. I've explained this quite a few times today. Multiply that by a solutions matrix. So let's call that y for now. What will this solutions matrix be? Well, with this linear form, the solutions matrix would just be the log of the Sherwood number, right? Yeah, because that's like the solution. This is like the y. This would be the b, and these are like m1, x1. This is m2, x2. So now we need to set up a design matrix, and then I think we'd be ready to just run this thing. So the design matrix is we're going to use something called numpy's column stack function. And that's just going to say, if we give it a tuple, it's going to take all the arrays in that tuple, and it's just going to put all the arrays going. First array will go up one column, second array will be another column, third array will be another column. So if you look at this, we have a constant plus an mx plus an mx. So we need to take this constant. So this is just going to be a bunch of ones, right? Because it's a constant, it's not changing over time. So there's another function we can use. It's called numpy. Numpy's just really help us out today. Ones like, come on. One's like, yeah. And we're just going to say it's like Reynolds number. The Reynolds number and the Schmidt number are identical dimension arrays, but we're going to call them the same thing. And then over here, we would need this numpy log of the Reynolds number, and then the numpy log of the Schmidt number. Once again, I'll just call that natural log, or at least I'll try to call it natural log. And then let's look at what constants gives us when we solve for it. Oh, it didn't like it. It takes one. Oh, okay, shoot. So I was supposed to give it like a matrix, basically. So I need to put these. I need to give it a tuple, rather. I needed to put in there. Yeah, so this is exactly what we wanted to see. So if you look at this, this would be like the constant A, the constant B, and the constant C. Well, the constant B makes sense, right? That's 0.83, 0.83. Constant C is pretty darn close. This is actually closer than you usually get. But constant A is super messed up, right? Why is that? Well, that's because what we really put into this design matrix wasn't the constant A, because the constant A right here, it's not just a constant, it's, it'd be like this 0.23, it'd be like the logarithm of this 0.23. So if we were to say that A is equivalent to constants of 0, so the first term of that, but it's going to be np dot exponential. So that's e to whatever power is inside the thing. That's e to this power. We go ahead and we'll maybe solve that in output A. We're going to see something very similar to the theoretical Sherwood value, what they have found, which is that number is close enough for us, even though it might not be close enough for chemical engineering in general. It's close enough for us in this situation. So then we could say that B is just going to be equivalent to the constants at 1, and then C is just going to be equivalent to the constants that matrix at 2, and we could just print that, and we would see, look at that, we would see the three values of A, B, and C that are about approximately the same as the A, the B, and the C in this Gilliam-Sherwood correlation. I'll actually write that in up here. So we have this Gilliam-Sherwood correlation. Once again, how am I doing on time? I'm sorry I keep checking this. I like the time I'm making, and I wanna get that in my head. I'm making great time. Yeah. Dang, my voice is kind of getting worn out, though. I don't know how long I'll be able to maintain the speed. So, let's see. We have just used the linear regression with the Penrose pseudo-inverse to determine these constants A, B, and C. But that's not all we're asked to do. We're also asked to minimize the sum squared deviation. So, what in the world does that mean? Well, I know what it means. I just have to think about it for a second before I explain it, so that way I can explain it a little bit better. And that's why I'm kind of stalling by saying this, just so my brain can kind of mull it over. Well, you know what, I'm going to stay on the same paint file, but I'm going to go over here. So this is the much more natural, but probably not actually as efficient way to solve some sort of issue like this where you're trying to generate something. So let's go back to your y equals mx plus b situation, right? We got an x-axis, we got a y-axis, and we got a bunch of points. So there's one right here, there's one right here, one right here, one right here, and one right here. So if we were, you know, back before computers and all that, you know, in the age of our forefathers, we would probably go ahead and change our color to red, and we would just draw a trend line, right? And we would say, okay, how good is this trend line? Well, there's kind of a difference here, right? There's a difference here, right? There's another difference here. There's only a little difference here and here, but there are some differences in these two. So we would add up all these differences, right? And then we would take the absolute value, or we could even square those differences. And yeah, we could use that to determine this trend line. This trend line gets maybe like a 5. Maybe it scores a 5 when we add all those numbers up. But if we drew a trend line, say, in blue, and we drew a trend line like this, well, then there'd be pretty high stuff right here, right here, right here. That would be closer to, like, I don't know, let's say that would be like a 15. That wouldn't be a very good trend line. We could say, okay, well, we're going to use the 5 trend line over the 15 trend line. So with that all in mind, we live in the age of computers. So instead of having to just guess and check this hundreds of times, we can have a computer that doesn't have a soul guess and check this hundreds and hundreds of times. So yeah, and this is called the sum. I don't like writing in blue. I like writing in black. I just think it's more professional. This would be called the sum square error, SSE. And we want to minimize it. So first off, let's go back up to the top and let us go to from this thing called SciPy. Very fun. He's going to help us out a little bit today too. SciPy.optimize. And from that, we are going to import, import, we're going to import, a function called minimize. So minimize, that's fun, that's awesome. I'm so glad we're able to do this. So how does minimize work? So minimize wants a, oh come on, you like it, you know you like it. Okay, now I'll change it to saved. Did I run this cell? I didn't run this cell. That's why it's not coming up with minimize. Yeah, now it is. So it wants a function, and remember that's a function. It's not a variable. It's a function, not a tuple or an array or something. It's a function, and then it wants some initial guesses for that function, and it's going to guess just a bunch of values. It's going to guess them over and over again until it gets whatever values leave that function as close to 0 as possible. So we need to define a function so that when we solve that function, this value is as close to 0. So it would pick the 5 over the 15. Hopefully it could even get it done like 2 or a 1 or, you know, maybe a 0. Although that would require perfect data, and the perfect data isn't going to happen. So we already have this linearized. So that's awesome. We already have it linearized. So that's pretty important. Let me go ahead and define a function. So we're going to define some square error, and we're going to define it in terms of these parameters. We have to define like parameters within a function. Now, the parameters are going to be they're going to be like the constants, right? They're going to be this A, B, I didn't highlight B, and then C, right? So we're going to call that one constants again. And then we need to return something. So we're actually going to return kind of the equation for the sum square error. So the sum square error, and I'm switching around a lot, but that's just the way I kind of want to do it. That's going to be the actual y value. So these points, the actual value of the points for each one, right? And it's going to be the summation of that. So it's going to be the summation. I'm going to just erase this x because you all get the meaning. You all get what I'm trying to accomplish here with that. It's going to be the summation of that, and then we're going to subtract. If this were in this situation, it's mx plus b. So that's our trend lines forecast, and then we're going to have to take all that, and within this summation, we're going to have to square it. Because remember, this one, the difference is kind of negative. This one, the difference is positive. So we're going to have to account for that. We could account for it by taking, say, the absolute value, but let's just square it. It won't really make a difference in the long run. So let's see what is from Numpy once again, really helping us out today. Thanks, buddy. We're gonna get sum, and sum all we really care about is this A right here. There's a lot of other just jargon we don't really need to worry about for what we're trying to do. And so we need the independent variable. So the independent variable is just the log of the Sherwood number. Remember, we have to keep this in a linearized form, so that way we can work this out in a linear formula. And yeah. So now we need to take the difference between these two things, but that difference needs to be squared. And it shouldn't be multiplied by 2, it should be squared. And then the summation is just going to sum it up for the whole array. Because remember, this NP log of Sherwood number, that's an array of 100 values. Right? So, yeah. So we need to subtract that, and I like everything I see so far. Oh no, I didn't like that. Did not like that. I didn't like that either. So yeah. Let's go ahead and say, okay. We'll just copy paste this in here, right? Because this is the, this is kind of the mx plus b, or it's more like b plus mx1 plus mx2. So yeah, but we can't use a, b, and c, right? We have to put it in terms of constants. So we'll say that a is constant 0, or the first term in this constants formula. Then constants 2 is going to be the second term in there. And then constants, the third c is going to be constants, or the third term in that variable, or in that, not in that variable, in kind of this tuple we're calling. No, it's not a tuple, is it? It would be like an array that we're calling constants, I think. I'm not certain. Can you see my hand when it's over here? Not really. My hand is just like, I do stuff with my hands, you know. I wonder, I did some stuff with my hands earlier. I wonder if you could see it. I hope you could, because it was pretty informative. I think, I hope everybody learned a lot from that. Anyway, yeah. So we got this minimize, and now we need to minimize the function above. So we're going to minimize the function sum square error. And we're going to minimize it for some initial guesses. We need initial guesses. You know, I think in the last video I made called Exam 1, I kind of explained the concept of initial guesses a little bit more. Here, I'm going to violate a rule I made earlier, and I'm going to pretend like I actually know what the values should be. So that way we don't have to go through a complex process to make initial guesses. So we'll just say that, oh, I think about 0.02 works for A. And then B, you know what, I think probably about we'll call it 7.5. That sounds about good for A. And 0.0, and maybe for this last one, we'll be a little bit more off. And we'll say the last one is 0.5. That would be our guess for C. So, yeah, let's see what minimize gives us. And he might not like it. Ooh, minimize didn't like it. But why didn't he like it? He didn't like it. Is this supposed to be in brackets, I wonder? I don't think it is. No, of course it's not. Silly me. Let's see. So he did not like it. We got this sum square error. There's a function. There is... Yeah, so let's see, did I do anything weird here? Well, let's go ahead and, run. Oh, okay. Oh, shoot, I forgot. But you know what? I forgot a parenthesis in there, but that parenthesis is probably... yeah, so these are obviously not the correct values. So I forgot a parenthesis in here, and it is going to ruin everything. It's not going to like it. So I'm going to get rid of that, because I want that to be right here. And I think if I run it now, there it is. Okay, so I put some of my parentheses in wrong. Once again, the way the parentheses are right now is actually correct. So yeah, we get a bunch of nonsense, then we get this x down here. This x is returning an array. And this array is, this is an array of the constants a, b, and c in that order. You see it's approximately the same as what we got up here when we solved the design matrix using linear regression, the Penrose pseudo-inverse. So we've just, through basically guess and check, just gone through and found the same thing that this matrix has done. So that's really cool. And, you know, if you think about this before the day of computers, yeah, this would have seemed pretty miraculous, right? I mean, it would have made a lot of jobs a lot easier. A lot of jobs kind of obsolete. So, yeah, we have this minimize function. Let's go ahead and set that equal to const constants. I know I'm getting caught up in the name of the variables, which I shouldn't, but I do. I am. I like it that way. I like my variables to be correct. Constants.x 0. So we're saying that a is the first value from the constant's array. And when I say dot x is basically saying call just this line of the output. Don't call the whole output. Just call that line. Just do that. Don't worry about the whole thing. So yeah, we'll go ahead and say b is the second value. Not the second. B is the second value, which would be value 1. And then copy paste that again. I like to just copy paste and change. I find that's easier for me to kind of keep up with. And then we will do print A, B, C. Yeah, look at that. So we have A, B, and C all printed. So, and it's about the same as these values. It's in the same format. So with all that in mind, we are ready to plot the trend line because now we have these values of A, B, and C, right? So now, instead of having like these, we think of these as like, okay, instead of being 0.023, it's more like 0.022-ish, you know, etc., etc. So, yeah, let's go ahead, let's come down here and let's separate these lines a little bit and let's put in our own code. So we're going to have to build a grid, right? Now, the way you make a grid is like, we could generate one line. It basically, let me think about this for a second to make sure I explain it correctly. I'm going to try something. So I'm going to take a screen cap of that. And then I'm going to go over here. I'm going to zoom out a little bit. And I'm going to do that. And then I'm going to zoom back in a little bit. I'm going to go down here. I'm going to copy paste that in. So we have that in here, right? We're going to say we want to generate a trend line, right? And we want the trend line. We want this trend line to look something like this. We want a grid of a bunch of lines. And we want a grid of a bunch more lines, and they're all going to intersect. It's going to look pretty. It's going to look a lot better than that. But how do we actually get there? Well, we need to basically generate a bunch of Sherwood numbers at a constant Reynolds number. And then we need to generate a bunch of Reynolds numbers at a constant Sherwood number to get each like set of lines in the array. So that's kind of how we want to get to the end product I showed you earlier. So that's a, you know, that's kind of novel and hard to understand, and it would be kind of hard to program out even. But luckily, NumPy is here to save the day once again. So we're going to say that Reynolds for grid purposes and the Sherwood number, or the Schmidt number for grid purposes, is equal to this sort of function. And it's a NumPy function called meshGrid. I spelled it wrong. meshGrid. Yeah, meshGrid, it likes it. So meshGrid, basically what meshGrid does is, yeah, it's mainly for creating grids, but it's going to take the first array you give it, and it's going to generate the second array relative to the first array. So we're going to give it a bunch of Reynolds numbers at first, and it's going to give us a bunch of Schmidt numbers relative to those Reynolds numbers. So Reynolds numbers should stay constant, Schmidt numbers should vary for this one. So how do we get the Reynolds and Schmidt numbers? Well, we don't want a bunch of random data this time. We want actual lines. So let's use linspace, which is a function I used in my last video. We used linspace a little bit. And linspace, what does linspace want? He wants a start, he wants a stop, and he wants a number to go, a number of things. So for Reynolds number, we'll say for Reynolds number on the grid, he probably wants to start at 2,000. He wants to go to 35,000. And we will give it 25 lines, maybe? I don't know. I think it's 25. I've done 20, I've done 25. I think you can do either and be okay. Now we need to generate this Sherwood number at the grid. So how are we going to generate that? Well, quite simply, we're going to take what we did over here, right? And using these constants we generated before, we are going to solve for the Sherwood number. So we can just do that. Now, after we solve for the Sherwood number, we need to start plotting it. Now, how are we going to plot it? How are we going to orderly pull the values from each of these grids and go through and plot each line separately? Plot like these 20 points and these 20 points, or it should be 25. You know what? I never wrote another function for the Schmidt number. That would have given me a major error. That might have been a little bit hard to diagnose, so luckily I caught it now. The Schmidt number, the range of the Schmidt number is from 0.6 to 2.5. That's something that they just determined probably through trend lines and R squared fitting and that sort of thing, linearity, etc. So now we need to use this for loop. So for a group of increments, the increments are going to be the Reynolds number increment, the Schmidt number increment, and the Sherwood number increment in a zip. Now, zip is a function built into Python that is just lets us combine arrays into one object, essentially. So it calls them iterables. No, I didn't mean to do that. I mean to copy. Sometimes I hit copy when I mean paste, and I hit paste when I mean copy. It's kind of unfortunate. So for that range, we are going to generate the plots. So fig dot add, no, not add annotation, silly goose. Fig dot add trace, and then we need the trace type. So go is short for graph objects. We're going to take the scatter 3D from go. And we are going to modify scatter 3D a little bit. Once again, what is scatter 3D like? He likes an X value. He wants a Y value, but he needs a Z value. And he actually needs all those to function. I don't know why I said it that way. I was just kind of being a little bit goofy, I guess. So we need an X, Y, and a Z value. Well, that's just going to be the Reynolds number, the Schmidt number. I almost said Sherwood, and the Sherwood number. So, yeah. And we're getting really close, too, for those of you who are concerned. Well, you can just look at the video time and see that we're close. I'm the only one who doesn't know how long the video is actually going to be, because I haven't checked the time in a while. But I'm pretty sure the video should be under an hour, which is nice. And I just got new internet in my apartment, so I don't have to go to campus to upload things in a timely manner, so that's pretty nice. So I'm really excited about that. But anyway, yeah. Now we have, we've created some traces, and it has these increments, and this increment is basically going to pull out the first value from Reynolds grid, the first value from Schmidt grid, and the first value from Sherwood grid. So let's just see what this looks like. And it's not going, oh no, it didn't like the syntax. Ooh, oh, because there's two equals signs. That is ugly. Oh no, I still didn't like it. It's because I can't spell grid. I spell gird, like bird, but with a G. So have I found all the errors now? It appears so. It's not giving me anything red, but the graph it generate might not make any sense, and then I'd be in trouble. But the graph it generate does make sense. But there's some huge issues with this, right? We have a legend over here, and it's not good. We also have points. We want lines. If you remember what we saw, we had lines initially. And also, I like the number of them, I think. I like 25 points, I think. But we also want them to all be the same color. That would look a lot better. So, how can we get there? Well, first off, similarly to how we set the mode to markers before, let's set the mode to lines this time. So the mode is equal to lines, and we'll set the line color. We're going to set that line color to, set it to blue. I like blue. It should fit pretty well with kind of the off blue that is the default color. And then the last thing we need to do is get rid of that legend. So we're going to do show legend, and that's going to equal false. So we run that, and let's see what we get. It's running. Okay, there it is. Look at that. So that's pretty cool, right? These are all our grid lines. They all fit together. They look like they fit pretty well, but we also look at these grid lines. So these are at a constant Schmidt number. So I said it wrong before. It's at a constant Schmidt number. We vary the Reynolds number. Okay, well, we want to go through and get lines that are perpendicular to these, right? We want to get lines that are at a constant Reynolds number. We vary the Schmidt number. So let's go ahead and do that. We can just copy paste this whole thing down, and yeah. We can just switch up the order here. So X, Control V. And we're going to switch up these mesh grids. X. We run it again, and we should get lines that go perpendicular to those lines, and something that looks like an actual grid. So we do that, and oh, that's not what I wanted. Something's off. Something's a little fishy. What happened here? Well, we got a Sherwood grid. We got... Okay. We have a gird here. Don't know why it's gird. He's not a very cool guy. He's kind of a jerk, in my opinion. We have a gird there, too. We'll change those over to grids. Once again, now it's just a simple typo. I understood the content pretty well, but just a simple typo. And now we have this generated, and look at that. This is the beautiful chart we were all waiting for that we saw at the beginning of the video. So this lets us totally visualize where the Reynolds number, where the Schmidt number, and where the Sherwood number change as you change them. Once again, all those Reynolds numbers, Schmidt numbers, Sherwood numbers are letting us learn about the viscosity, the velocity, the driving force, and how all these things relate to each other. So with this in mind, how much time do I have? How much time have I used? Hey everybody, sorry about that interruption. And it's kind of silly. I was looking at the recording thing, and I thought that I hadn't hit record, or something was just wrong with the recording. Luckily, the recording's all fine, and it all looked good to me, so I'll probably end up uploading that one. But yeah, I just wanted to go through and maybe talk a little bit more about this, and I think everything I already covered pretty much answers all parts of the exam, but I wanted to go ahead and add a little bit more. So let's say that instead of adding, say, 100 points, we actually did 1,000 points each, right? So we changed this both to 1,000. Let's say instead of having a 0.1, like a 10% standard deviation, we had a 1% standard deviation. So we run all this, we go down here, and it's going to take a while to run the graph because it has 10 times as many points to plot. But look at that. We actually get a number, and we have a lot more points, and they're a lot closer to the actual trend line. But yeah, this just goes to show, I think this is kind of just a cool thing to be able to visualize a little bit. Yeah, so that kind of goes to show that. Now, let's say we had all the way down to let's say we went up to a 0.25. Let's say we increased. We went back down to 100 data points. Let's say we had a 25% standard deviation, so a lot higher of a standard deviation. Oh, dang. Okay, so I meant for something else to happen, I guess. I meant for there to be... I'm going to try going up to 50 then, maybe. I don't know. Let's see. We got this. Yeah, look at that. That's pretty interesting. So, yeah, there's all these points, and the trend line is not quite as clean now. And if you look at this, our initial guesses are a little bit... Well, they're actually still pretty good at the end of the day. Our initial guesses are, but let's say we went pretty crazy. We had pretty bad data. There's a 40% normalized random error. And it still got the right... It still likes it? What? Yeah, so you're really starting to see things break down here, I would say. But let me go ahead and... Come on, I'm trying to break this. It's so easy to break it normally. I think if I just run this again... No, why not? Okay, I'm going to... Let's say our random guesses were 0.3 or something. Yeah, so that's kind of the issue with returning the sum square error, is that your guesses, you would have to modify them every time. Let's just go ahead and define A, B, and C as that. And we'll run that with just the A, B, and C from the Penrose pseudo-inverse. And, yeah, I was just trying to demonstrate some of maybe the inflexibility, at least in this situation, of the sum square error. Even though it's a little bit easier to conceptualize, I think, it isn't always as useful. So we have all these kind of a cool little effect with the grid here. It's like a wave or something. It's kind of hard to explain. But yeah, that's pretty much all I had to say. So yeah, thanks for watching, and I hope you learned something. I certainly learned a lot, and I hope that this was able to help you or really answer the question well. And yeah, I hope everybody has a nice day, and thanks for watching.